Hello and welcome to this revision session for AQA A-Level Physics. We're going to look at paper 1 in this revision session. So if we are successful in this revision session, we should be able to answer examination questions from A-Level Physics paper 1. So we should be able to assess our understanding on A-Level Physics and then understand what topics we need to improve upon in this paper. So how should you carry out this revision session? So when completing your work in this revision session, divide your paper into two sections. Make the left hand section larger than the right hand section. So in this section, write down your working out and answers to the questions in the revision session. Now when you're doing this, make sure you write out in full sentences and show your working out. Whilst on the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you carry out revision for A-Level Physics? Well, the first step is knowledge. Learn the key facts. Use the revision guides, the class workbooks, the student prep notes, a textbook to learn the key ideas of the course. Now to do this, you might want to make mind maps or write out the notes yourself. Step 2 is retrieval. Testing yourself. So use things like Caboodle, Seneca, a knowledge checker to quickly test your own knowledge. Now you may wish to do this from your own cue cards. While step 3 is practice. So you would do practice examination questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. And you may wish to download your own examination past papers to do this. So there are 3 steps for revising A-Level Physics. Learn the key facts, then test yourself, then practice examination questions, which is what we're going to do in the next section of this revision session. So the first area we're going to look at is particles and radiation. So, more than 200 subatomic particles have been discovered so far. However, most are not fundamental and are composed of other particles including quarks. It has been shown that a proton can be made to change into a neutron and that protons and neutrons are made of quarks. Name one process in which a proton changes to a neutron. Name the particle interaction involved in this process and then write down an equation to the process you stated in the first section and show the baryon number and lepton number are conserved in this process. So pause the video now and then unpause the video when you want to go through the answers. So, first question, name a process that turns a proton into a neutron. Now you just need to know these key facts of what processes do what. So a proton to a neutron is going to be electron capture and beta plus decay. As a note, now you're at A-level, don't just say beta decay as that's too vague. It's either beta plus or beta minus decay. Now a neutron to a proton is beta minus, but a proton to a neutron is beta plus. Now the particle interaction involved in this process. Now we know a proton is changing to a neutron, which means the quarks are changing flavour. The only interaction that can do this is the weak interaction. Now the next bit is you've got to show that the baryon number and lepton number are conserved in this process. Now to do this, you've got to show that the total baryon number before is equal to the total baryon number afterwards and the same for the lepton number. So that involves you learning the different baryon numbers of the different types of particles of baryons, leptons and mesons and then writing it out as shown here. Now again, you've got to show that the total number before equals the total number afterwards. Right, next question. The strange quark was used to explain the existence of particles whose tracks had been seen in experiments in the early 1950s. These were unexplained at that time and were referred to as strange particles. One of these particles was later named the K plus kaon. State the quark composition of the K plus kaon. Then a K plus kaon decays into a pi plus particle and a pi zero particle. Explain one property which is conserved and one property which is not conserved in this decay. So, pause the video now, then unpause the video when you want to go through your answer. So, let's see how you answer these questions. Now the first thing to note is that it's a kaon, which means it must have either a strange or an anti-strange quark, as that is the definition of a kaon. Now you then got to look in your equation book and look at the charge of the quarks and antiquarks and look at the baryon numbers of the quarks and antiquarks. Now because it is a kaon, we know it's a meson, so it's one quark, one antiquark. So you've got to find a quark-antiquark pair which will give a charge of +1 because it's K plus, and a barrier number of 0 because it's a meson, and also includes either a strange or an anti-strange. So the only two that will do this are up and anti-strange. Now it says next that a K plus decays into a pi plus and pi 0. Now what is conserved in this decay? Well, you've got to know that energy mass, momentum, barrier number, lepton number and charge are always conserved in every decay. So that is the one that is conserved. Now because we're dealing with a kaon which has a strangeness, that does not have to be conserved if the decay is via the weak interaction. So we know that the answer could be charge or barrier number, lepton number, momentum, energy mass for conservation, but not conserved is strangeness, which is 1 before and 0 afterwards. Right, next question. The photoelectric effect can be demonstrated by illuminating a negatively charged plate made from certain metals with UV light and showing that the plate loses its charge. Explain why, when ultraviolet light is shone on a positively charged plate, no charge is lost by the plate. Then calculate the maximum kinetic energy in joules of the electrons emitted from a zinc plate when illuminated with ultraviolet light. Then explain why this answer is a maximum. Pause the video now, then unpause the video when you want to go through the answers. Right, so the first idea is it's the photoelectric effect, which is when electromagnetic radiation is shined on a metal surface and the metal surface emits electrons. So you've got to have the idea that electrons are emitted and then negatively charged. So therefore any process involves the ejection of negatively charged electrons, and removing a negative charge will only make a positive charge greater, which is why it won't lose any charge because it's getting a greater positive one. Next one is you're going to have to calculate the kinetic energy. Now the first thing to do in this situation is you'll notice you've been given a value of energy for the work function, but it's in EV. So you need to convert that value of EV into joules, which you do by times by 1.6 times 10 to the minus 19. So you work that out and it's 6.9 times 10 to the minus 19 joules, and then you remember the photoelectric effect equation, which is that the photon energy, HF, is equal to the work function plus the maximum kinetic energy. So what you can therefore do is say that the maximum kinetic energy is equal to HF, the photon energy, minus the work function. So the photon energy is H, Planck's constant, times by the frequency, given in the question to be 1.2 times 10 to the 15 Hertz, minus the work function in joules. That gives us an answer of 1.0 times 10 to the minus 19 joules. Now why is this value a maximum? Well, it comes from the definition of the work function. The work function is a minimum amount of energy to remove an electron from a metal surface. So if the energy splits between the work function and the kinetic energy, if the work function is a minimum, the kinetic energy is a maximum. You also could have said that because we define the work function as the minimum amount of energy, so therefore the electrons are emitted from the surface of the metal. So therefore if the electrons are emitted from a deeper part of the metal, they would have less kinetic energy. Right, so the next question. Complete the following table which compares the properties of the positive pion and the proton. When a positive pion interacts with a proton, a kaon can be produced along with another strange particle as shown in this equation. Circle the type of interaction shown in this equation, and then deduce the relative charge, barrier number and strangeness of particle X. So pause the video now, and then unpause the video when you want to go through the answers. Right, so for the first one, you've just got to know the properties of a meson, which is a pion, and a proton, which is a baryon. So therefore we know that the charge of a proton is +1. Remember that from GCSE. Now we should also know that a pion has a barrier number of 0 because it's a meson. So all mesons have a barrier number of 0, and that the proton is a baryon, so there's a barrier number of 1. Now to work out the quark composition, what you want to do again is remember how many quarks should be present. So for a proton it's a baryon, 3 quarks. For a meson, quark, antiquark, and you've got to find the quarks in the back of the examination booklet, which will add up to give a charge of +1 for both of them. So you can work them through as that. So you can see it's up, anti, down for the pion plus, whilst it's up, up, down for the proton. Now in theory you should actually memorize the value, the quark composition of a proton to be up, up, down. Now the next one, look at the type of interaction which is this particular equation. So we've got pion plus a proton goes to a kaon plus an X. Now we'll notice here that we've got no leptons involved, so it's not going to be via the weak interaction, and we've got a decay taking place, so it's going to be the strong nuclear, as electromagnetic and gravitational do not cause particle decays. Now reduce the relative charge, baryon number and strangeness of particle X. So what you've got to do in this case is, because we know that the decay is taking place and we know it's via the strong interaction, this tells us that the charge before and after must be the same, this baryon number before and after should be the same, and actually the strangeness before and after should be the same. If it was the weak interaction, the strangeness can change by 1, but you've just indicated that it's the strong interaction. So what you know is that the charge, firstly, well, we know that pi plus is going to be a plus because it tells you in the question. You know a proton is 1, and you know the kaon is plus is going to be 1. So therefore the charge of X is going to equal 1. Now we know the pion is a meson, so it's got a baryon number of 0. We know the proton is a baryon, so it's a baryon number of 1. We know the kaon is a meson, so it's a baryon number of 0. So therefore X must equal 1. And then finally for strangeness, we know the proton and the neutron must have a strangeness of 0 because they don't contain a strange quark in them, and therefore the kaon is a charge of plus 1, so X must be minus 1 to keep that conservation. Next question. Particle X can decay to produce a neutron and positive pion as shown in this equation. Circle the type of interaction that's shown in this equation. Then explain your answer. Then the neutron and positive pion will then decay. The positive pion can decay into a positron and an electron neutrino. Write down the equation for the decay of the neutron, then explain why no further decays occur. Pause the video now, then unpause the video when you want to go through the answer. Right, so the first answer, it is via the weak interaction. Now why is this? Well, there's 3 tells as to why something could be the weak interaction. Either there are hadrons and leptons present, which they're not at the minute. We could have the fact that there's a quark changing flavour, which we don't actually know is taking place at this point, because it could be the X particle could be splitting into 2, so we don't know it's actually changing the flavour of anything. But the third one is that the strangeness is changing by 1. Now we know that X has a strangeness of -1. You just worked it out in the previous question. Now a neutron and a positive pion have 0 strangeness. We know this because they don't have strange quarks in them. We know the positive pion is up, anti-down from the previous question, and you should memorize the neutron is down, up, down. So therefore the strangeness is changing by 1. So therefore it must be via the weak interaction. The next one is drawing out the decay with your symbol. So N goes to a proton plus a beta minus plus an anti-electron neutrino. Now why do no further decays occur? Well, you look at the products. Now, firstly, you look at the proton. Now, the proton is the only stable baryon present, so no decays will occur further. And secondly, electrons or positrons and the neutrino antineutrinos are leptons, so therefore, and they are the least energetic leptons, so therefore they're the most stable leptons. So because we've got stable products, no further decays occur. Let's look at the next question. State what is meant by the threshold frequency of radiation in the photoelectric effect. Monochromatic light with a photon energy of 3.7 times 10 to the minus 19 joules is incident on a metal surface. Photoelectrons with a maximum kinetic energy of 5.7 times 10 to the minus 20 joules are emitted from the surface. Calculating EV, the work function of the metal. Now the total power of the monochromatic light incident on the surface is 1.3 times 10 to the minus 2 watts. Calculate the maximum number of photoelectrons that can be emitted from the surface per second. So pause the video now, then unpause the video when you want to go through your answer. So you need to know the definition of the threshold frequency. So what's it linking with? It's the minimum photon frequency or minimum radiation frequency that allows an electron to be emitted to allow for the photoelectric effect to occur. Next one, we need to use that photoelectric effect equation, but this time we need to make the work function the subject. So like we said previously, HF equals work function plus maximum kinetic energy. So now work function is going to equal the total energy, which is given at there, so 3.7 times 10 to the minus 19, minus the kinetic energy, 5.7 times 10 to the minus 20. So you work that through, and it's 3.1 times 10 to the minus 19, but you then got to convert that value of joules into EV. Now, when you're going out of SI, and joules are SI and EV is non-SI, you divide by the conversion factor. And the conversion factor, like stated before, is 1.6 times 10 to the minus 19 joules. So 19 there. So as a result, we work that through and get our answer of 2.0 EV. Now the next thing to note is that we know that because we have the total power of 1.3 times 10 to the minus 2 watts, so a watt is a joule per second, so we can say that in 1 second, so per second, the energy is going to be 1.3 times 10 to the minus 2 joules in total. But we also know that one photon is providing an energy of 3.7 times 10 to the minus 19 joules. So we can therefore say the number of photons is the total energy divided by the energy of one photon, so therefore it equals 3.5 times 10 to the 16. Next question. Light is replaced with a different monochromatic light with half the wavelength but the same incident power. Describe and explain any effect on photoelectrons. So pause the video now, then unpause the video to go through the answer. Right, so you've got to know the effect of intensity and frequency on the emission of photoelectrons. So what do we know about how wavelength and frequency link together? So because we know C equals F lambda for radiation such as light, that if we halve the wavelength, we've got to double the frequency to keep C as constant. So halving the wavelength doubles the frequency. So that tells us that the electrons will have a higher kinetic energy because the frequency determines A, if the electrons are emitted, if it's above the threshold frequency, but B, how fast they are emitted with, how much energy they're emitted with, how much kinetic energy they've got, how fast they are travelling. So the photoelectrons have a higher kinetic energy because each photon has double the energy. But it's important to note that half the number of photoelectrons are emitted. Now why is that? It's because we've said it's the same incident power. So if the power is constant but each photon has double the energy it had before, well therefore you've only got half the photons hitting the surface. So therefore, because we know in the photoelectric effect it is a one-to-one interaction, one photon to one electron, that if we have half the photons, half the number of electrons are being excited by the photons, so therefore only half the number of electrons are going to be emitted because only half the number of electrons have absorbed a photon. So therefore there's two effects, that the electrons are emitted with a higher kinetic energy, so are moving faster, but there's only half the number. Always read all the information in a question when you answer it. So let's now have a look at a few questions on mechanics and materials. So the figure 1 here shows a golfer hitting a ball from the top of a cliff. The ball follows the path shown. The ball is hit with an initial velocity of 40 meters per second at an angle of 30 degrees above the horizontal. Assume there is no air resistance. Now calculate the initial vertical component of the velocity of the ball. Then draw on the diagram to show an arrow to show the direction of the force acting on the ball when it's at point X, the highest point of its flight, and label this F. So we'll pause the video now and unpause the video when you want to go through the answer. Right, so it's asking to calculate the vertical component of the velocity. So you've got to know how to derive the vertical component and horizontal component of vectors. So what you would do is you draw a right angle triangle with the 40 as the hypotenuse and the 30 as the angle to the horizontal. What you then do is you can use SOHCAHTOA to work out that vertical height, that vertical side on your right angle triangle, and so therefore we can say that it's going to be the sine 30 is going to equal opposite over hypotenuse, so sine 30 equals the vertical velocity over the overall velocity, so therefore vertical velocity is equal to the overall velocity 40 sine 30 equals 20 meters per second. Now let's draw the where the direction of the force acting on the ball is going to be at point X. So the highest point of flight is going to be a vertical line labelled downwards. Because in a projectile such as this one, the only force acting on it will be gravity, which is acting downwards. Now in the next one, at point Y, the ball is level with its initial position. Show that the time taken to reach Y is about 4 seconds, and then the total time of the flight of the ball is 6 seconds. Show on figure 2 how the vertical component of the velocity changes throughout the whole 6 seconds. Right, so pause the video now, then unpause the video when you want to go through the answers. Right, so the first one is you're going to have to use a equation of motion because we're going to have a constant acceleration. So you could use the equation v equals u plus at. Now how I would tend to do it is write out SUVAT s, u, v, a and t, see what you have. So you will have your value for v, your starting value, you'll have u, you'll have a, and you need to work out t, so you would use v equals u plus at. If you had s, you might want to use another equation of motion, but you've got to write it all out and see which equation of motion fits. So therefore you can write it out. So we say v equals u plus at. Now it's important to note that what we're going to do is we're going to work out the time it takes to reach the highest point, because at the highest point we know that at that instant the velocity is going to be 0. So we can say that v at x is going to equal 0. We know that u equals 20 from the previous question. I know the acceleration is minus 9.81. Why is it minus? Well, it's minus because we're accelerating upwards, because we're going upwards, yet the acceleration due to gravity is downwards, so we're going to say it's minus 9.81. So we're going to say 0 equals 20 minus 9.81 times by t. We therefore know that t is going to equal 2 by rearrangement, and so that's to x, but then to get to y you're going to have to double it, because that's only half the journey, so therefore it's going to be 4.08 or 4.1 seconds. Right, in this next one we know a few things. We know that we're starting our velocity at 20. I suppose you could also say it's minus 20 depending on how you define it, but let's say we'll start at 20, and then we know that we're going to have the constant acceleration going on, because we've got the only force acting on it to be gravity, which is unchanging. So that tells us we're going to get a straight line, because it's a constant acceleration. It's going to be a constant acceleration, and the gradient of a velocity time graph is acceleration, and we know it's going to start at 20, and we know that it's going to decrease, because as it's going further and further up, it's going to slow down until after approximately 2 seconds it's going to equal 0, before then increasing in velocity after we get past 2, when it gets to about 4, but it's also going to go to a negative velocity, because before x is going up, after x is going down. So therefore, because we've got different directions, we've got to denote that in physics with a plus and a minus, because different directions are denoted by pluses and minuses. So as a result, you should get a line which is a straight line, which then starts at 20 or minus 20 and crosses the x-axis at approximately 2. Next question. From this information, calculate the height h of the cliff. So pause the video now, then unpause the video when you want to go through the answer. Right, so we're trying to work out height, which is going to be basically the displacement of the entire journey, because if you notice, we're starting at the top of the height and we're going to finish at the bottom of the height. So in that previous question, you look here, we drew a velocity time graph. Now we should be able to be aware that the displacement is actually the area under the line of a velocity time graph. So as a result, you can work out the area under the velocity time graph you've just drawn, and that will equal 60 meters. The other way you could do it, instead of using the graph from the previous question, is you could once again use your equations of motion. So what are we trying to work out? The displacement, s. What do we know? We know u, because it's going to be 20 to start with, because that's our vertical velocity, and we're only working in the vertical because we're trying to work out the vertical displacement. We know what time is, because we know that we can work out the time from the previous values, and then we can know what a is going to be. It's going to be 9.81, so we can say v equals ut plus a half at squared, and work out our answer to be approximately 60 meters. Next question. A car is designed to break the land speed record. The thrust exerted on the car is 230 kilonewtons in one instance of its motion. The mass of the car at this instance is 11,000 kilograms. The acceleration of the car at this instant is 2.9 meters per second squared. Calculate the air resistance acting on the car. The thrust on the car remains constant as the speed increases. Explain why the acceleration decreases and eventually reaches 0. Then finally, a supersonic car is a attempting to break the land speed record on a horizontal track when it is travelling at 320 meters per second. A small part P that is 1.3 meters above the ground becomes detached from the car. Calculate the initial vertical velocity of P. It's 2.5 meters per second in the upwards direction. So calculate the time taken for the small part P to reach the ground, assuming that air resistance has a negligible effect on the vertical motion. So pause the video now, then unpause the video when you want to go through the answer. Right, so the first thing we're going to note is we're trying to work out the value of air resistance, and we've been given an acceleration and we've been given a thrust exerted on the car. Now, what do we know? So firstly, that we can say that the resultant force is going to equal MA. Now we've got M, which is 11,000, and we've got A, which is 2.9. So we can work out straight away our resultant force, F, which is equal to MA, is going to be 31900 newtons. Now we also know that the resultant force acting on this car is going to be the thrust going forward minus the air resistance going backwards. So therefore the air resistance is going to be equal, if you ever think about how you then rearrange it, is going to be equal to the thrust minus the resultant force, which you can work it all through, and then you get an answer out of approximately 198,000 newtons. Now the thrust on the car remains constant as the speed increases. Explain when the acceleration decreases and eventually reaches zero. Well, this links into Newton's first law of motion, which is the idea that a resultant force causes an acceleration. So as the speed of the car increases, air resistance increases as well. So this therefore means the overall resultant force is going to decrease as speed increases, because the difference between thrust and air resistance is getting smaller and smaller. Then eventually air resistance will equal thrust, so there's no acceleration and you've reached a maximum constant velocity. Now we don't call that a terminal velocity because it's not falling. Now the next one is calculate the time taken for the small part P to reach the ground. So what you can do is as follows. So you can take the time to reach the maximum height. So we know that it's going to be 2.5, which if you look in the question is going to be the initial vertical velocity, divided by 9.8, which is going to be the acceleration due to gravity, so that's then 0.255 seconds. So therefore the maximum height, which is then another Suvat equation, is therefore working through by 1.5 plus 4.9 times by 0.255 squared. So you get that to be 1.82 meters. So the time taken to reach the ground for the maximum height is therefore going to be 0.61 seconds. So therefore you add that together, time to reach maximum height to reach the ground to be 0.87 seconds, or you could use another equation of motion, but you'd have to use it as a quadratic to then solve your values. So you could do the equation S equals ut plus a half at squared, then work out t, but it is a quadratic, but you'll be noticed that if you solve that value via a quadratic method, you'll get a positive and a negative value. You can't get a negative time value, so it has to be the positive one. Now it's important to note you always select your equation of motion very carefully. Write out S, U, V, A and T, see what values you have, then use the appropriate equation from what you need to get from what you've already worked out. Right, next question. So figure 3 shows that the path P would follow from the instant it became detached if there was no air resistance in the horizontal direction. In practice, air resistance is not negligible in the horizontal direction. Draw on figure 3 a line to show the path that P would follow, assuming that air resistance only affects the motion in the horizontal direction. Then explain your answer, including the reason why air resistance is negligible in the vertical direction. So pause the video now, then unpause the video when you want to go through your answer. So, first thing to note is that it's going to start at 2.5 meters per second. So you'll notice here, you can see that the height above the ground is still going to be 1.5. Okay, now the maximum height reached is the same, but it's going to be earlier, and then it's going to have a range which is a lot less than 175 meters, a lot smaller because of the air resistance. Now it's important to note that it's not going to affect it because the motion is unchanged vertically and the maximum height is unchanged, but air resistance decreases P horizontally, so there's then less distance travelled, and then air resistance increases with speed. Now again, in the vertical the speed is low but high in the horizontal, so it's not going to be a factor in the vertical, but it will be in the horizontal motion. Right, next question. A signal flare that is a projectile is launched into the air from a stationary boat to attract attention in an emergency. The signal flare ignites at the top of its trajectory. Figure 4 shows the trajectory of the signal flare to the point which it ignites. The signal flare is launched with a vertical component at 58 meters per second from a point 5 meters above the sea level, assuming that its weight is the only force acting on the signal flare after it has been launched. So calculate the maximum height above sea level reached by the signal flare. Show that the time taken for the signal flare to reach the maximum height is approximately 6 seconds. Then the signal flare is launched at an angle of 70 degrees to the horizontal. Calculate the horizontal distance of the signal flare from its launch point when it reaches maximum height. So pause the video now, then unpause the video when you want to go through the answer. So let's have a look at answering this question. Now again, we're trying to work out the maximum height reached by the signal flare. So we're going to have to use an equation of motion. So you can do SUVAT, S, U, V, A and T. Now we're trying to work out S. We know what U is going to be because it's told in the question. We know what V is going to be again because we can work it out from the question, and we know what A is going to be because the only force acting on is weight, so the only acceleration is due to gravity. So we can therefore use the equation V squared equals U squared plus 2AS, and then pop in the values. Now again, we'll know that it starts off with a U of 58 because that's what tells us in the question. The value of V at maximum height is going to be 0 because at maximum height it's got no speed, it's got no velocity. We know what A is going to be. It is going to be 9.81, so therefore you can work through your value for S, which is 176 meters. Another way of doing it, by the way, is using energy conservation. So you could say mgh equals a half mv squared and then work out h because you've got V, and the m's cancel through and you know what g is. So it's another way of doing it. Question 2. Again, how can you work this out? For the maximum height, the signal flare is approximately 6 seconds. So you can do it by either one of two ways. You can either say that acceleration is going to be the change in velocity over time, or that we can use an equation of motion. So we either use V equals U plus AT, or S equals U plus V over 2 times by T, because we know what U is, we know what V is, and we know what T is now. So as a result, we want to work out T, and we know what S is from the previous question. So we can work it all through, and we get 5.91 seconds. Next one, calculate the horizontal distance of the signal flare from its launch point when it reaches the maximum height. So what you can do is now you can work out what our equation to work out the horizontal component of the velocity is going to be. Now we can work that then through, and then we can use the equation speed is equal to distance over time, or velocity is equal to displacement over time. So therefore our displacement is equal to the horizontal velocity, which you can work out by resolving the horizontal component of the velocity. Now just be careful, the reason why we've used tan 70 in the mark scheme is because they give us the vertical component of the velocity, which is going to be 58 meters per second, not the resultant. So we're going to have to use our right angle triangle and then work out that we're going to have to do tan theta is equal to opposite over adjacent because we've not been given the hypotenuse in this example. So we've worked out the horizontal component of the velocity with that methodology, and then we've used the equation displacement equals velocity times by time. We can do that because there's no force in the horizontal, the only force is in the vertical, weight. So therefore we don't need to use an equation of motion, because if there is no acceleration, because there's no resultant force, we can just use the equation velocity equals displacement over time, and we get our answer to be 125 meters. Next question. Figure 8 shows a section of a suspension bridge. The bridge deck is supported by a single cable attached to a vertical tower. Figure 9 is an enlarged view of the cable and the top of the tower. The cable makes an angle of 40 degrees to the horizontal where it meets the tower. The tension T in each section of the cable is 1.2 times 10 to the 8 newtons. The weight of each cable is negligible. So part 1, calculate the magnitude of the resultant force exerted on the tower by the cable. Then the mass of the tower is 7.1 times 10 to the 6 kilograms. Calculate the magnitude of the reaction R of the ground on the base of the tower. So pause the video now, then unpause the video when you want to go through your answer. Right, so first thing we're going to have to do is calculate the magnitude of the resultant force exerted on the tower by the cable. So what you're going to have to do is then going to have to look at resolving your particular forces. So we know that the tension of each section of the cable is 1.2 times 10 to the 8 newtons. So we can therefore say in theory that we're going to have T sine 40 is going to give us our vertical component. So as a result, we can then work that then through. So say T sine 40, where we know what T is 1.2 times 10 to the 8 newtons, is 1.5 times 10 to the 8 newtons. Working it through like that. So again, it's important to note that we're going to have to draw a right angle triangle and resolve our components correctly. Then the next one is we're going to have to work out the magnitude R, so the magnitude R of the ground on the base of the tower. Now it's important to note that because we're going to have a steady tower, there's going to be no resultant force in the horizontal or the vertical. So the reaction up is going to equal the weight acting down. Now you've got a mass which is 7.1 times 10 to the 6 kilograms. You then convert that into the weight. So therefore we know, okay, that we've got a value here of approximately 2.2 times 10 to the 8 newtons, and working it through like that. So we can work that particular value out. Next one. A car of mass 1,400 kilograms starts from rest and travels along a horizontal road for 90 meters. Figure 10 shows the variation with distance of the resultant force on the car. So describe the motion of the car over the 90-meter journey and then calculate the initial acceleration of the car. So pause the video now, then unpause the video when you want to go through the answers. Right, so you can notice straight away that we've got force on the y and distance on the x. So what's going to happen with acceleration? Well, the resultant force is directly proportional to acceleration. So you can see in your graph that the resultant force is increasing, therefore the acceleration is going to increase with time or with distance, either one you want to say. So therefore calculate the initial acceleration of the car. Well, we've been given a distance, we've been given a resultant force, and we've been given a mass. Now we do know from Newton's second law, F equals ma, so A equals F over m. Now m is 1,400 and F at the start is 0.2 kilonewtons. So we then convert that into newtons, so therefore we know that's 200 newtons, so it's going to be 200 over 1,400 kilograms, so it's going to be 0.143 meters per second squared. So next, show that the useful work done accelerating that same car over the 90-meter journey is about 2 times 10 to the 5 joules. Calculate the speed of the car after it's travelled 90 meters, then discuss how the resistive forces experienced by the car change over the 90-meter journey. So pause the video now, then unpause the video to go through the answers. Right, so if you notice, we've got a force against distance graph. Now you should hopefully remember or look in the back of the equation book to know that work done is equal to force times by distance. So that's therefore telling us that if work done is force times by distance, that the area under the graph of a force distance graph is going to be the work done. So what you're going to have to do to then show that the work done is about 2 times 10 to the 5 is work out the area under your line of best fit of your graph. So you can work that through. Now you can do it via two methods. I would personally split it up into two particular shapes. I would split it up into a triangle by doing a half base times height at that section, and then from 0 to 0.2 then do that very small rectangle and add the two together. Next one, calculate the speed of the car after it's travelled 90 meters. Well, what we've got is we've got a mass, we've got a distance. We can also work out, we've got an energy in there because we've got a work done, and we know that it's starting from rest and work is being done on it, so it's going to have a kinetic energy. So we can use all that to work out its velocity, because we know kinetic energy is going to equal a half mv squared. So therefore we've just worked out the kinetic energy because it's the work done on the car. We know the mass is 1,400, and we can rearrange the equation to make v the subject and work out our answer to be 17.2 meters per second. Then finally discuss how the resistive forces experienced by the car change over the 90-meter journey. Well, it's the idea that friction will always stay the same because it's the same between the car and the road, but the air resistance increases with time because the speed is getting higher, so there are more air particles colliding with the car every second, so therefore the air resistance increases. Right, let's now have a look at a few questions on electricity. So the first question. Figure 6 shows the current voltage characteristic of a lamp used in a car headlight up to its working voltage. Draw on figure 9 the characteristics that will be obtained with the connections with the supply reversed. Then lamps are marked with their working voltage and power used at this voltage. For example, a light for use in a torch may be marked as 2.5 volts and 0.3 watts. Deduce the marking on the lamp for the car headlight. So pause the video now, then unpause the video when you want to go through your answer. Right, so you should be aware that for a lamp it's going to reflect that same shape, but it's going to be in the bottom left hand quadrant. So you have the same general shape plotted to about a half a square to reflect, so it's going to be in that bottom left hand quadrant. Now the next one is you're going to have to deduce their working voltage and power. So we need to know what the working voltage is going to be. So it's going to be the highest voltage shown, which is going to be 12 volts. Now you'll also note that the current at that working voltage is 2.5 amps, which you can see from that particular graph, and we know power is V times by I. Hopefully you can know that, but it's also on the equation sheet. So it's going to be 12 times by 2.5, which you can work it through to therefore be 30 watts. Next one, determine the resistance of the lamp when the potential difference across it is half the working voltage. Then, explain without further calculation how the resistance of the lamp varies as the voltage across it is increased from 0 to its working voltage. So pause the video now, then unpause the video when you want to go through your answer. Right, so you know that resistance is equal to V over I. Now at half the working voltage, now we know that half the working voltage is going to be 6, because we know the working voltage, which is the highest value, because it tells us in the question it goes up to the working voltage, is 12. So therefore half the working voltage will be 6. So R is equal to V over I. So it's going to be 6 over 1.9. Now we know it's 1.9 because we look on our graph and we go up on 6 volts and we see I at that point is 1.9. So it's 3.2 ohms. Now what's going to happen to the resistance as the voltage is increased? Well, the resistance is going to increase. We know this because the voltage is going to increase, so therefore voltage and resistance are directly proportional. So if V is going up, R is going up. But why is that? Well, as resistance goes up, the temperature of the component increases, so therefore there are more collisions between the charge carriers, the electrons, and the ions of the metal lattice. Next question. Figure 3 shows a thermistor T used in an alarm circuit for a refrigerator. The alarm is designed to sound a buzzer B when the temperature exceeds a threshold value. B has a constant resistance of 123 ohms. The battery has a negligible internal resistance. The buzzer sounds when the potential difference across it is greater than 1.8 volts. Explain why the potential difference across the buzzer increases when the temperature increases. Then show that when the potential difference across the buzzer is 1.8 volts, the resistance of the thermistor is about 80 ohms. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you need to be aware of is the idea that of how a thermistor works. So as the temperature increases in the circuit, the resistance of the thermistor decreases. So you could argue that there's more charge carriers available for conduction. So because when a thermistor has its temperature increased, it releases more charge carriers into the circuit. But also it's important to note that V is directly proportional to R. So that's telling us that when R goes down for the thermistor, for T, V, the proportion taken by T, is going to go down as well. Now because this is a potential divider and we know that EMF in equals PD out, the total value of 3 is going in, so a total value of 3 is going out. So because T is taking a smaller proportion of it because it's got a smaller value of R, well then the only other thing that can take the higher proportion of it is going to be B. So therefore B will take a higher proportion of the battery potential difference. Now, show that when the potential difference across the buzzer is 1.8 volts, the resistance of the thermistor is about 80 ohms. Well, what do we know? Well, we know that if the potential difference of the buzzer is 1.8 volts, well, therefore the potential difference of the thermistor is therefore going to be 1.2 volts because the total is 3, because there's 3 in, so 3 in total is going out. So therefore the potential difference of the thermistor is 1.2 volts. We know that the current is going to be the same through both, so we can say to work out the current we can then, if we know that The buzzer has a resistance of 123 ohms at the start of the question. We know its value of V is 1.8 volts, so we know that V equals IR, so therefore I is equal to V over R, so it's going to be 1.8 over 123, so it's 0.0146 amps. So if it's 0.0146 amps through the buzzer, it's going to be 0.0146 amps through the thermistor because they're in series with each other. So we know what I is. So we've got V, which is going to be 1.2. We've got I, which is 0.014 amps. So therefore R is V over I, and we can work it out like that to be 82 ohms. Next question. Figure 2 shows that 3 identical resistors, each with a resistance R, in a circuit connected with the cell with EMF 1.5 volts. The cell has a negligible internal resistance. When switch S is closed, the reading of the ammeter A1 is 1.2 amps and the reading of ammeter 2 is 0.40 amps. State that the value of current I1 when the switch is closed. Then calculate R. Well, let's pause the video and then go through the answer, unpause the video. Right, so the first thing to note is that we can work out what the value of V is going to be in that particular circuit, because we know that there's an easy way of doing that, is that if A2 is going to be 0.40 amps, and we know that the total A1 is going to be 1.2 amps, if the total is 1.2 and the second track is going to be 0.4, well, that first track must equal 0.80 amps because the current before a junction equals the current after a junction. So after the junction, it's going to be 1.2, so it's going to be 0.4 plus something else, which is 0.8. So therefore, calculate R. So what we can now say is we now know in that first track here, we know that the value of I is 0.80 and we know the value of V is 1.5 volts because in that first loop, in that first track, EMF in equals PD out. So the EMF in is 1.5 volts, the PD out is 1.5. So therefore say R is V over I, so it's therefore going to be 1.5 over 0.80, so it's going to be 1.9 ohms. Next question. Switch S is returned to the open position. State and explain the effect this has on the readings of A1 and A2. Pause the video now, then unpause the video to go through the answers. Right, so let's have a think about each one. So what's going to happen to A1? Well, if we close that particular if it's returned to its open position, what do we know about the total circuit resistance, which is what A1 is measuring, because A1 is measuring the total circuit like we saw in the question before. Well, if we've now gone from a parallel circuit to a series circuit, the resistance is going to get higher because now there's only one path for the charge carriers to go through. So because the resistance has increased, the value going through A1 will decrease. Now, what's going to happen to A2? Well, A2 is only going to be looking at that second track. Now, in that second track, in that second loop, the potential difference hasn't changed because it was 1.5 before and 1.5 after, because different loops in parallel circuits don't affect each other. And what's going to happen to the resistance? Well, the resistance for this branch is going to be the same because it's just those two values in that series track with that A2. So because we know that PD and current are the same, the value of A2 is going to be constant. I mean, the other way you could say it is A1 is going to equal A2 because now they're both in the same series circuit because we're taking out that first track there. So now our series circuit is going to, our total resistance of that series circuit is going to be 2R because we've got two resistors, each of 1R. So therefore, the current is going to be 0.40 amps to work it through. So A1 has decreased whilst A2 has stayed the same value. Next question. Figure 8 shows X connected to two other lamps, Y and Z. All three lamps have identical IV characteristics. Explain for this circuit how the resistance of Y compares with the resistance of X. Calculations are not required. So pause the video now, then unpause the video when you want to go through the answer. Right, so let's have a think about what's going on in each one. So what's going to happen with the resistance of Y compared to the resistance of X? Now Y is in a parallel circuit whilst X is just in a series circuit in general. So it's the idea that Y is going to receive less current compared to X, because the current is going to split when it gets to the junction after X, so it's going to split between Y and Z. So we can say quite clearly, because Z will have a resistance because it's identical to Y, that less current will pass through Y than it will do X. Now this therefore means that at these lower currents or voltages, okay, that the resistance is going to be less. Now you can also think about this because we know that Y will have a smaller voltage than X. Why do we know that? Well, it's because we know that the voltage will split between X and that parallel component of Y and Z because it's there in a potential divider configuration. So whilst they're splitting, X will get half of the total volts because we know that because all three are identical, whilst Y and Z will have to share some. So therefore, actually, Y is going to have less volts as well. So because there's less volts going through Y, there's less resistance. So therefore the resistance of Y will be lower. I mean, you can also say because at lower currents, there's going to be less resistance. So Y has less resistance than X. Right, so let's have a look at this question. Figure 2 shows a circuit containing two fixed resistors, a variable resistor and a battery with negligible internal resistance. Voltmeters V1 and V2 are connected across the fixed resistors. The resistance of the variable resistor is increased. State and explain how the readings on V1 and V2 are affected by this change. So pause the video now, then unpause the video when you want to go through the answers. Right, so what's going to happen when the resistance of this variable resistor is increased? Well, let's talk about V1 first. Well, because we know that they're in this loop with the battery, we know that the rule of circuits is that for a loop in a parallel circuit, EMF in supplied by the battery is equal to PD out over your components. Now, there's two of them here. Now we also know that V is directly proportional to R. The reason for this is because when you're in that loop, the current is the same in the loop. So therefore, to maintain a constant current flow, if there's a greater resistance, you'll need more energy per charge to push the charge through that particular component and maintaining the same rate of flow. So therefore, V is directly proportional to R. So what this means is that when the resistance of the variable resistor goes up, it is taking a greater proportion of the battery's EMF because it's got a greater value of R, so its V it's taken is going to be larger. So therefore the resistor next to it for V1 is going to take up less of a voltage because more is taken by the variable resistor, so the value in V1 goes down. Now it's also therefore important to note as well that in a parallel circuit, different loops don't affect each other because in terms of V, because they each draw the value of EMF from the battery. So therefore, because 15 is going into that first track or loop, for example 15 volts will also go to the second track or loop, so therefore V2 stays the same because the resistance of the variable resistor won't affect that second track because the tracks don't affect each other. Now you say that V2, because it's the only component in that track, in that loop, it will take all of the battery's EMF, so we'll keep on doing that because it's the only thing in that loop. So I hope you've enjoyed this revision session where we'll try to answer examination questions for AQA A-Level Physics. So I hope you can answer those examination style questions. You can assess your understanding of A-Level Physics and understand what topics you need to improve on for A-Level Physics. Thank you very much for watching this revision session on AQA A-Level Physics Paper 1. Thank you very much and have a lovely day.